fourth video in this series. This series is the Learn Machine Learning video series, and in today's video we will be talking about machine learning classifiers and specifically decision trees. So today's video will be covering a lot, and there will be a coding tutorial on how to build a decision tree. So I guess sit tight, make sure to drop a like on the video and subscribe to the channel. Once again, this is the fourth video in the series. Today we're covering machine learning classifiers and decision trees, and let's get started. So we will begin the video by giving a general introduction with machine learning classifiers and how they are used. Let's get started. What is a machine learning classifier? A machine learning classifier is a type of machine learning algorithm that helps us to predict between discrete or categorical values. What do I mean by a discrete or categorical value? For example, with the machine learning classifier that classifies the color of a car, the discrete or categorical value would be the color of a car. The color of a car is a value. It's a category, right? A car can be blue, it can be yellow, it can be orange, it can be red, etc. So since these different output values are categories or discrete, they are considered categorical values. In other words, these types of machine learning algorithms are trying to predict the class of a given data point. And the class is the key word here, because we're not predicting a continuous output. We're predicting a very discrete, categorical class type of output. As you can see in the graphic, there's just some examples of classifiers: decision trees, logistic regression, SVMs, neural networks, and random forests. These are some of the most dominant classifiers used in today's machine learning. And throughout the video, we will discuss the roles of some of these classifiers, specifically decision trees. How does a machine learning classifier work? A machine learning classifier uses supervised learning to learn a discrete value function f from the input data. To really break this down, what's going on here is that supervised learning, like always, works on trained and labeled examples. What's a labeled example? In other words, supervised learning works with input and output pairs. We need both input and output for the model. In other words, we're mapping a function f from the input variables x to discrete output variables y. The graphic below illustrates an example of the supervised learning process for classification. We have training data, apples and cupcakes. We train it into a machine learning model where we create a function that can distinguish between unseen and unlabeled data, and then we are able to output a class, like cupcake for example, for some unlabeled data example. This is really the broad process, the very high-level understanding of how supervised learning, specifically for classification, works. And throughout this video, we'll really understand how we really create that function to map from input to output. And so far, this is really just a review from what we've talked about in earlier videos. So right now, we're just discussing how supervised learning is really the foundation for some of the most important machine learning classifiers, like decision trees. Let's talk about an example of a classifier. The spam-no-spam paradigm is a classic example of the role of a machine learning classifier. This classic machine learning problem is where a machine learning classifier must be made to distinguish between emails that are spam and not spam. Spam emails are emails that are useless, typically advertising or junk email. Not spam emails are emails that are useful and must go in your inbox folder. So we need an algorithm that can clearly distinguish and differentiate between the two and place not spam emails in inbox and spam emails in the spam folder. So the way this would work is that we would utilize some training data to understand how the given input variables relate to the class. And as you can see in the image, we basically train based off spam and not spam emails, and the classifier generally learns using supervised learning to distinguish between the two, and thus for output places the spam emails in a spam folder and the not spam useful emails in the inbox folder. So there is an example of the role of a classifier, like in the spam or not spam example. Let's talk about what types of learners are in classification. A learner in classification is the algorithm which discriminates between the classes or categories of variables. There are two types of learners, lazy and eager learners. Let's first talk about lazy learners. Lazy learners are types of machine learning algorithms which simply store the training data and wait until a testing case appears. What does this mean? This means an algorithm which actually quickly compiles all of our training data and then makes a first prediction when the first testing data case appears. What does this mean? This means less training time since all the training data is already stored, but takes more time to predict because we have to wait until a testing data case appears. An example of a lazy learning algorithm, k-nearest neighbors. And k-nearest neighbors is a machine learning classification algorithm that classifies based off votes from local neighboring data points. So lazy learners, the idea here is that we have all of our training data, we're waiting for some kind of a testing case, and this translates to less training time but more time in predicting. Let's talk about eager learners. Eager learners are where we construct a classification model based on the given training data. And this is all before we receive data for classification. What does this mean? This means more training time and less time for predicting. Remember, going back to lazy learners have less training time but more time in predicting. And in this case, we have more time for training and less time in predicting. Why is this important? In an eager learning algorithm, we immediately construct the classification model off the training data, but our training data doesn't come immediately. It's not already compiled like in lazy learning. In this eager learning, we're basically training off of a very large data set, but then it takes much less time to predict. Thus, this is much more of a heavy, broad-scale algorithm. An example of an eager learning algorithm is a decision tree, like the one shown in the description below. And it's really important to be able to distinguish between lazy and eager learners because those are the two types of crucial classifiers that are used in machine learning. And if you can understand the behavior behind these algorithms, then it makes much more sense how they work on a visual basis. Now let's jump into different types of classifiers that exist in the machine learning community. Let's talk about decision trees, one of the main focuses of today's video. A decision tree classifier is a classifier that's based on a set of if-then trees, or a Boolean rule structure. The example given in the image is a really good example of a decision tree. The top node, the root node, asks the question, is the salary at least $50,000? Remember, the overall premise for this decision tree is, should I accept a new job offer? If yes, if true, we move to the next decision node. The next decision node is the commute more than 1 hour? If yes, that's not a good thing, right? So that's false, and we decline the offer. If no, false, and it offers free coffee, which is our next decision node, then we can either accept the offer or decline the offer. So decision trees really work like human behavior, right? When humans think, they also really break down into these subtrees and these subnodes, right? So decision trees are a really good example of a classifier that's based on Boolean logic. And the way we make a decision tree is using what we call top-down recursive divide and conquer structure. And what this means is that you're recursively iterating through a decision tree to create all these graphical nodes. And in this case, it's really important when we talk about decision trees to understand some key terms. There are nodes, there are leaves, and there are branches and subtrees. And we're going to go into decision trees in much more depth towards the end of the lesson, but for now, it's just important to understand that the basic premise for decision trees is that it's based on Boolean logic, right? It's a set of true-false pathways. And for now, it's just really important to understand that the decision trees are all about the true-false segmentation that makes them up. Let's talk about naive Bayes. And so naive Bayes is a probabilistic classifier. So it's dependent on whether the attributes are conditionally independent. That's what a probabilistic classifier means. And it's called naive Bayes classifying because it's based off Bayes' theorem for probability. What does Bayes' theorem for probability say? It basically says that the conditional probability of a certain outcome or event is based on the past probabilities of that event. It's completely conditional. And so since Bayes' theorem revolves around conditional probability, naive Bayes models are also completely based off of conditional probability and conditional independence. This equation here, where the probability of x given ci is basically summation of all the conditional probabilities of those events. Therefore, to understand naive Bayes on a very high level is to basically understand that it's a probabilistic classifier that is dependent on whether attributes are conditionally independent. And I don't believe that this is the greatest explanation of naive Bayes. It does take a little bit more mathematical and probability intuition, but we will cover this in a future lecture. Let's continue. The next type of classifier I want to talk about is the artificial neural network. This is the new hot trend in deep learning today, and artificial neural networks are really, really popular in regard to their applications for computer vision, for robotics, for health processing, health data processing, etc. And the way these artificial neural networks work is that it's a set of connected input-output units where each connection has a weight or an associated amount of importance to that unit. And these networks are comprised of many hidden layers And the way that the network learns or is able to compute output is that it learns by adjusting the weights, or these hidden connections. And in this example of a neural network in this image, you see how the different features of a building are really important for its output, which is the estimated formwork labor quantity, or amount of men it's going to take to build the building. And the crucial thing to understand about neural networks is that it's all about adjusting those weights. It's the iterative process. Last video we talked about, I believe, linear models and all those different kinds of regression models that we can use for machine learning. And when we talked about those models, we talked about gradient descent. And gradient descent is a really important concept because it's the iterative process of reducing the loss by traveling down the gradient, the loss gradient. And I believe that the process of artificial neural networks behaves a lot like gradient descent because both have really similar learning algorithms. Gradient descent works by adjusting the learning rate and adjusting those hyperparameters that we talked about, whereas artificial neural networks works by adjusting weights and the different input-output nodes that are involved in the process. So that's another example of a really interesting classification model. And we will go much deeper into artificial neural networks in the deep learning videos later in this series. The last type of classifier that I want to talk about today is the k-nearest neighbor. This is a lazy algorithm that stores all instances corresponding to training data points. And what's important about k-nearest neighbor is that it analyzes the closest k number of instances saved. In other words, it analyzes the nearest neighbors. And based off of the nearest neighbors, it picks the most relevant class. So this lazy algorithm is actually really interesting because it has lots of applications for many different fields. And the name actually makes a lot of sense, right? It's k-nearest neighbors. You're taking a data point, you're examining its k-nearest instances, or the surrounding neighbors to that data point, and based off those neighbors and their classes or categories, you're picking the most relevant category or class for the current data point. And therefore, this algorithm is really intuitive, and just like the classifiers I talked about in these cases, we will talk about k-nearest neighbor in much more depth in a future video. So now let's go into depth with today's main classifier, which is decision trees. And we're going to really break down the process of how to make a decision tree, what goes behind a decision tree, how do they operate, what are their advantages, disadvantages, etc. And let's break it down. So we've talked about these other classifiers, but I really want to go into depth on what is special about decision trees. Decision trees are special because they work with discrete valued outputs. In other words, you don't find regression trees. Regression trees are really rare. Most decision trees are based on discrete valued or categorical outputs, right? Like comparing cats versus dogs, not really predicting the housing prices in the Bay Area. Those are two completely different problems. And for the second one, for the latter, with the housing prices, it's really rare that you would find a regression tree. So what I'm saying is that in most cases, decision trees are almost always discrete valued outputs. Why are decision trees special? They can represent multiple Boolean functions. And another reason why decision trees are really cool is that a decision tree algorithm is able to transform the data itself into a completely different structure, right? So decision trees take a problem, they take a certain data set, they take a certain predictive problem, and they model it completely differently. In other words, you're creating a completely different structure from the original problem. And that's why I think decision trees are really innovative, because the algorithm is able to transform the data and parameters itself. And it turns it into a tree like the one that's shown here, where there's a decision node or a root node at the top, and it just keeps on branching into subtrees with leaf nodes that break into more decision nodes, etc. That's why I think decision trees are a really cool classifier to talk about, because they really represent what we can do with machine learning and take it to the next level. And let's talk more about it. So now let's jump into how to build a decision tree. It's a pretty simple process, but I think this is a really simplified way to talk about it, actually. And in reality, it's not this simple, obviously, but this is kind of the general schema for building a decision tree. So step one, you're going to start at the top of the tree, and you're going to start by splitting attributes one by one. You're then going to assign leaf nodes to the majority vote. In other words, you're going to look at your neighbors, look at the tree above you, and based on that, you're going to assign the leaf nodes the majority class or category. You're going to go down, you're going to prune the tree at the bottom. We haven't talked about what pruning the tree means yet, but we will talk about it really shortly. And pruning the tree, in essence, is all about preventing overfitting. We haven't talked about overfitting yet either, but overfitting is a really bad thing that could happen to machine learning classifiers. So we prune the tree in order to prevent overfitting, and I'll explain what pruning means later. And what I want you to understand here is that when we build a decision tree, it's a completely top-down structure. It's also really important to understand that it's recursive, right? So remember, we don't build a tree by starting at the bottom and working our way through different subtrees. We start at the root node at the top, and we recursively iterate through all of our subtrees, assigning the majority vote, splitting attributes, pruning at the very bottom leaf node until we've gone through every single subtree. So remember, this is the top-down recursive process. That's what I want you to understand here. Let's do an example of a decision tree because I feel like so far we've gone really theoretical, but now I really want to consolidate our understanding to a concrete example. So the problem that this decision tree solves is the question, will I play tennis today? Just like any machine learning supervised learning problem, we want our features and labels. Our features in this case are the outlook, the temperature, humidity, and wind. And the given categories for each are given on the slide. And our label or our output is basically yes or no, right? When we play tennis today, it's either a yes or no answer. It's a positive or negative. So this is, in other words, a binary classification task. And if you recursively iterate through these examples and you use common sense to figure it out, then you get something like this, where you start at the top with some features, you work your way down, and through each of these yes-no trees or true-false Boolean trees, you can basically get to a final yes or no answer for whether you want to play tennis today. And this is what the intuition behind decision trees is. It's really just you're taking your features and labels, creating a structure to represent the relationship between the features and labels, and then mapping or running through these features and labels in order to get the output or the label. So this is how decision trees work. So I brought up the term overfitting earlier, and let's talk about why overfitting is a really big problem with decision trees, and why it's crucial to prevent overfitting with a decision tree. So overfitting occurs when our decision tree algorithm has better accuracy on the training data compared to the test data, or unseen data. Why is this bad? So we have these three graphs here on the bottom. And so we have an underfitted graph, we have a good fit or robust graph, and we have an overfitted graph. It's pretty clear to see that in the overfitted graph, this is bad, because we've fit our data too much, in other words. This is overfitted, right? And this is bad because on our training data, this works great, because we trained with our training data, right? But when we provide test data or unseen data, then this is actually really inaccurate because it's that the model itself doesn't actually correspond to real life, right? It's just completely biased to the training data. And in real life, there's going to be unseen data that may not look like that, right? So that's why overfitting is really bad, because it's a form of variance or bias that can really harm the accuracy of your model. And underfitting also occurs with decision trees, but it's much more rare. I think overfitting is the bigger problem. And I brought up pruning earlier, and that's why pruning is so important. Pruning is the way by which we prevent overfitting or reduce it in a decision tree. And the ideal goal with all decision trees or all machine learning classifiers is to get to that good fit or robust fit for the model, where you're not really overfit, but you're not really underfit, right? You have a good amount of variance. It's not completely biased. It's not like has zero bias, but it's a relatively well-fit model. That's the goal. And we prevent overfitting with the decision tree by pruning the decision tree. So what does it actually mean to prune a decision tree? To prune a decision tree means to remove its leaves and assign the majority label of all the parents to all the items. This is kind of a really technical definition, I'd say, when you're actually building a decision tree and pruning it in the same process. So I think to simplify this, what we're doing is that we're reducing the dimensionality of a decision tree when we prune it. By dimensionality, I mean the size. We're reducing the dimensions of a decision tree. So this is an example in the image that I've given on the slide. So on the left, you have a pre-pruned decision tree, and on the right, you have a pruned decision tree. As you can see, after you prune the decision tree, we lose some of the subtrees. And this is good because this is what we want to do, right? We don't want to have overfitting become a consequence, right? And so that's why pruning decision trees is so important. That's what the takeaway here is. We prune decision trees to prevent or minimize overfitting. That's the goal. What are some advantages of decision trees? An advantage of decision trees is that they're really easy to interpret, right? Decision trees are pretty common sense. Like in the one I've given here, where we're talking about cashing in or investing or funding, decision tree makes a lot of sense, right? It's a yes or no, true or false process. It makes sense, right? Yes, no, no, yes, etc. And why is this good? It mirrors human decision-making processes, right? So when we get to neural networks, I think we've already talked about the artificial neural network today, but artificial neural networks are also really interesting because they mirror our biological synapses and our networks of neurons in our body. So I think the connection between machine learning and reality is that lots of machine learning models and different schema in the machine learning community actually really closely mirror human views, some of the human processes we use, and that's why I think it's really useful to visualize these decision trees because they really mirror our thinking process, right? Like when you actually want to go somewhere, you want to go play tennis, right? You do use that kind of thinking process. It does make sense intuitively. So that's why I believe decision trees are really easy to understand, and they play a really big role in our decision making processes. And best of all, they're easy to visualize, right? For any kind of decision tree, you can usually write it out in a set of branches and trees. And in industry, decision trees, classifiers, they get really big, right? Like these are the ones I've given in this lecture are really simple and easy to understand, right? But in industry and in real world applications, when you have a decision tree classifier, it's gonna be really large, right? So these are relatively simple ones, really simple ones. So these are easy to visualize. But in general, no matter how big, you can always visualize a decision tree, which is a great thing. And as we'll see later in this video series, some machine learning and deep learning models are particularly difficult to visualize, right? Like with neural networks, sometimes neural networks behave like a black box. You can't really see what's going on inside of them. So that's why I believe an advantage of decision trees is that they're easy to visualize. And hopefully that makes them easier to use for you and for any kind of industry application. So let's actually take a step further, and we're going to talk about using a decision tree with Scikit-learn. So let's jump into that. So decision trees with Scikit-learn. Today's problem is being able to classify whether a fruit is an apple or orange based on two features. And so the goal here is to use the decision tree algorithm classifier in order to solve this problem in a few lines of code with Scikit-learn. And so some software prerequisites are Anaconda, Scikit-learn, a text editor, and that's not the issue though. The issue is let's figure out how to deconstruct this problem. We're given training data here, and we want to classify the fruit as apple or orange based on the two features, right? The features are weight and texture, and the label output is either going to be apple, orange, or apple. And in this example, the weight and texture are only two features, and it's important that we understand the relationship between the features and labels before we move on to coding this algorithm. So let's take a look here. A fruit that has a bigger weight and is bumpy is usually orange, whereas a fruit that is usually smaller weight and smooth is an apple. So it's pretty quick to realize with this problem that there's a very distinct relationship between the weight and texture and the label. It's not really a random process, right? There's a reason these are our two features. So I think now that we understand the relationship that fruits that are more smooth and smaller weight are apples, and fruits that are bumpy and larger weight are oranges, we now have an intuitive understanding of the problem, right? So we could represent this as a decision tree, and that's what we're going to do in our code. And let's code this algorithm. Let's get started. All right, so let's code this. And so we need Scikit-learn. So let's do from sklearn import tree. Cool. Now I want to import our features and labels. And we're not really going to import them. We're just going to set a variable or a tuple of features. And I'm just going to use the data that's here. So 140 smooth. So we're going to do smooth is 1. Bumpy is 0. And now let's just use all our features. So 141, 131. What's the next one? The next one's going to be 150 grams bumpy, which is 150, 0. It's arbitrary which one you set as 0 and 1. It just, as long as it works. And the last one is 170 and 0. Perfect. So those are our features. Awesome. Now we want to do our labels. So we're going to set another array to our labels, and we're going to store this as, I believe, so let's do this one by one. Number 1, the first feature pair in this set is the fruit that is 140 grams and I believe smooth. What is this? This is an apple. So let's just denote, before we start, let's just denote apple is 0, orange is 1. It doesn't matter which is which, it's just that we have to be consistent. So this is an apple, so the first one is 0. The next one's also an apple, that's 0 too. The last two are oranges, so we set those. So there we go, we've set our features and labels, and that's a great start to this problem. So now we've imported our structure as a tree, we have our features and labels set. Next we want our actual decision tree classifier. So we're gonna set CLF as our variable to set it, and we're gonna do tree.decision tree classifier. Awesome. There we go. Perfect. And so now what we've basically done here is that we've just initialized a certain decision tree classifier, the most basic type of decision tree classifier, a tree structure. Awesome. Now let's fit this to our data. We have our features and labels, and I want to fit it. So we're going to use a fit function. I'm going to fit it between features, labels. Awesome. It's that simple. Great. And to test this algorithm, I want to just print the result of testing it on some arbitrary value. Let's do a test case. What do we think a fruit that is 190 grams and bumpy would be? Well, based on our training data, even though the training data is really limited, it's still almost always be orange, right? Because it's a large weight and it's bumpy. Let's do that. Let's try predicting that. And bumpy. Awesome. And so I'm not actually going to run this code, but it should work. And I think the idea here is that, as you can see in like 5-6 lines of code, we've just coded a machine learning classifier from ground up. We have our features or labels, and we use a decision tree classifier. And even though we didn't actually create the decision tree classifier from ground up, we did fit it to our specific data, right? And that's why Scikit-learn is so useful, right? It's a framework that provides these already coded functions for like decision trees, k-nearest neighbors, regression algorithms, etc. That's why Scikit-learn is useful. And as you can see, in 5 lines of code, we coded a really cool decision tree classifier. And that's awesome. And I guess we're done with the code there. Let's finish the lesson. What are the takeaways from today? Today we discussed what makes classifiers so special, right? We talked about why they're different from regression algorithms like the linear models and stuff. We talked about the types of classifiers, right? We talked about decision trees, we talked about k-nearest neighbors, artificial neural nets, and naive Bayes. And all these classifiers bring something special to the table, right? For decision trees, it's that Boolean preordained true-false subtree structure. For k-nearest neighbors, it's the fact that you're searching the local instances of a very similar data point. Artificial neural networks is adjusting the weights to learn the input to output connection. And naive Bayes is all about using probability theory based off of conditional probability loops. And today we really went into depth with decision trees. And we talked about how decision trees use trees with leaves and nodes based on Boolean logic, like true-false logic. And at the end, we were able to implement a really cool but simple decision tree classifier in Scikit-learn in barely 5 to 6 lines. So that's really cool, and I think that should wrap it up for today. And that's it. Thank you guys for watching. Make sure to drop a like on the video, subscribe to the channel. This is the 4th video in the series. The next video will be much more advanced classifiers, and we'll probably also do a coding tutorial. So thank you guys for watching. It's been a pleasure, and I'll see you guys next time. Thank you very much.